This is Algebra 2, Unit 12, Probability and Statistics, and today we're going to talk about Lesson 1, Simple Probability, the counting principle, and factorials. All of this stuff, except for I think factorials, will be reviewed. Some important definitions about probability. First of all, outcome is the result of a single trial. The sample space is a set of all possible outcomes. An event is one or more outcomes of a trial. An independent event is when one choice does not affect another one. For example, if we've got a cooler with a bunch of different drinks in them and we pick one drink out, that has a certain probability. But then if we decide, okay, I don't want that one, I'm going to put it back in the cooler and pick something else, well, that first pick didn't affect the second one because you put it back in the cooler. Now, a dependent event, however, if you did not replace that drink in the cooler and you picked another one, that would be a dependent event because the second pick does depend on what the first one was because it affects how many are in that cooler. And so when you're doing probability, sometimes you'll be asked if it's independent or dependent and then asked to find the probability based on what the problem says. So let's just quickly look at some simple probability. There are two possible outcomes to flipping a coin, heads or tails. And the event of tossing a coin one time, if we toss a coin one time, probability of your result being heads is 1/2, and the probability of being tails is 1/2. So these are two separate coin tosses. Sometimes, though, we're going to be talking about a sample space for tossing a coin two different times. And in that situation, you have to think about what happens the first time and what happens the second time, and think about how many possible outcomes there are in that. So, for example, with the first toss, we would either get heads or tails. We can't get both. So we would, in the first toss, get either heads or tails. And then the second toss, it's independent of the first toss, but if we're talking about the probability of each of them together, we have to think about that probability separately. So for toss number 2, we could, if we got a head the first time, then the second coin should be either a head or a tail. If we got tails the first time, then our second toss would be either, again, a head or a tail, leaving us with 4 possible outcomes of this particular double coin toss. We could get both heads, we could get a head then a tail, we could get a tail then a head, or we could get both tails. So there are 4 separate possible outcomes for tossing a coin 2 times. And so then I could ask you, what's the probability of getting one of each? Well, out of the 4 times, there are 2 probable outcomes that give you one of each. So that would be 2 out of 4, or 1/2. The probability of getting 2 different outcomes each toss is 1/2. What if I say, what is the probability of getting both heads? Well, that would be 1 out of 4. What's the probability of getting both tails? Well, that again would be 1 out of 4. What's the probability of getting a head then a tail? 1 out of 4. What's the probability of getting the same thing both times? Well, they could both be heads or they could both be tails. So that again would be 2 out of 4, or 1/2. Let's talk about rolling a simple die. When we have a die, we have 6 sides. The possible outcomes are 1 through 6. And let's talk about the 6 possible outcomes in specific probabilities. Like, find these probabilities. What is the probability of rolling a 2? Well, there's only 1 2 on the 6 sides, so the probability of rolling a 2 would be 1/6. What's the probability of getting a 0? Well, the die has numbers 1 through 6 on the 6 sides. There is no 0, so that's not possible. So the probability of that happening would be 0. What's the probability of rolling an odd number? Well, on the die, there are 3 odd numbers, 1, 3, and 5. So that would be 3 out of 6, or 1/2. What's the probability of rolling a number divisible by 3? Well, if you think about numbers divisible by 3, those are numbers that 3 will divide into without a remainder. So 3 divided by 3 is 1, 6 divided by 3 is 2. So there are 2 numbers that are divisible by 3 on the die. So that would be 2/6 or 1/3 when you simplify it. What's the probability of rolling a number divisible by 1? Well, think about that. Isn't every number divisible by 1? 1 divided by 1 is 1. 2 divided by 1 is 2. Any number divided by 1 is itself. So the probability of rolling a number divisible by 1 is going to happen every single time. So that's a 6 out of 6, which gives us a probability of certainty, which is 1. So let's talk a little bit more about independent and dependent events. Suppose you have a bag with 5 red, 4 blue, 7 green, and 2 yellow marbles. Find the following probabilities and determine if they are independent or dependent events. Find the probability of drawing a yellow. There are 2 yellows in the bag out of how many total? There are 18 marbles in the bag. So we have a probability of getting 2 out of 18 for a probability of yellow, which is 1/9. And let's think about that. Is 1/9, is that probability of drawing a yellow? Does that depend on anything else happening, or is that going to be an independent event? Well, since we're only drawing one time, that would be an independent event. So I would put an I for independent. 2, what's the probability of reaching into the bag and picking out either a red or a blue marble, one or the other? Well, there are 5 red and there are 4 blue, so that's 9 out of the total 18. So 9 of 18, or 9 over 18, would be a 1/2. And if you think about whether that is a probability that is independent or dependent, well, did it say to draw once and then draw again? Or did it say just draw once and either one could fit this probability? It's that second one. We're only drawing once. So whether we get a red or a blue is an independent event. We're only drawing once, so that first draw is not affecting anything else. So this one is, again, independent. Look at 3. We want to find the probability of drawing a red, then a blue without replacement. In other words, I'm going to reach into the bag, draw out a red. Well, let's think about that. There are 5 red out of the total 18 in the bag. So if I draw a red, the probability of it being red is 5 over 18. And then it asks me to draw a blue without replacing that last marble. Well, if I don't replace that last marble, aren't there only 17 left in the bag to choose from? So I have 4 blue marbles out of the 17 that are left. So the probability of getting a blue marble is 4 out of 17. So now, to get the probability of both of these events together, what I have to do is multiply these two probabilities together. So my probability of drawing a red then a blue without replacement is 10 over 153. And this one is dependent because my second draw was only possible by depending on what we got here, because that second number, the number on the bottom, changes because we did not replace. Had that first marble been replaced and then we drew, then it would be independent. But this one did depend on the other one because the number inside the bag decreased, making this one a dependent probability. I forgot to finish typing this one. What's the probability of drawing a green, then a red with replacement? So we're going to replace the one that we draw the first time. Well, the probability of drawing a green is 7 out of the 18 in the bag. And then if we replace that one, we now still have 18 in the bag. If we draw a red out of that, we would have a 5 out of 18 for our probability of drawing a red. The probability of both of these things is what we get when we multiply those two things together. And that is 35 over 324. And since the first marble was replaced, this is an independent event. Number 5, drawing 2 blue without replacement. Okay, so I'm not going to replace this time. So I'm drawing a blue the first time. So that would be 4 out of 18. Well, 4 out of 18 simplified would be 2/9. So for my first draw, I have 2/9 because there are 4 blue in the bag to begin with. So 4 out of 18 is a 2/9 for my first draw. Then for my second draw, I have to consider that I'm not replacing. So instead of having 18 in the bag, I have 17. So whatever I get will be out of the 17. And think about this. It says they are both blue. Okay, we had 4 blue to begin with. We've already drawn 1 blue. So now we only have 3 blue left. So the probability of getting a blue the second time when the first one was also blue is 3 3 out of 17. We're going to multiply these two together to get the final probability. And that gives us a final probability of 2 over 51. That's a 1, not a 7. So 2 over 51. Now we have to determine, is this independent or dependent? Well, this one by itself is independent, but then when we add this second one to it, or we multiply by the second one, it becomes dependent because we did not replace the marble. So this one, what we get here, depended on what we got here. So this one is a dependent event. All right, suppose you have a die and a coin. What is the probability that you will roll a 6 and a tail? Okay, so if we roll a 6, well, the die has 6 sides. One of them is a 6. So the chances of rolling a die and getting a 6 is 1/6. Probability that we get a tail with a coin is 1/2. So our final probability is going to be 1/12. There's no way rolling a die and flipping a coin have anything to do with each other. They are completely independent events. So let's move to the fundamental counting principle. Remember the sample space that we had when tossing 2 coins. We said that the first toss could be heads or tails. And then we said that the second toss could be heads or tails as well, but the difference between our sample space for just one toss and our sample space for 2 tosses is we have to consider what happens first and second. We have 4 possible outcomes for that event. Both heads, a head then a tail then a head, or both tails. So this becomes our sample space due to the fundamental counting principle. And there's a simple way to do this without having to draw this tree diagram. If we had to draw the tree diagram for every one of these, it would take forever. But here's a simpler way. If all they're asking us for is how many outcomes are possible, then all we have to do is take how many outcomes are possible with toss 1. And if you think about tossing a coin, there are 2 possibilities, head or tail. So for the first toss, it's a possibility of having 2 things. Then for the second toss, there's a possibility of having 2 things happen. If we just want to know how many things are in our final sample space, how many outcomes are possible, all we have to do is multiply these 2 things together. And this is known as the fundamental counting principle. We take how many outcomes are possible for the first event, how many outcomes are possible for the second event, and then we multiply those 2 things together. So here's some real simple examples on this. So we're going to use the fundamental counting principle to try to figure this out. Find the total number of outcomes for a family having 3 children. And we could draw a tree diagram. So we're talking about child 1, child 2, and child 3. Okay, now the second child is not affected by the first child. And the third child is not affected by the second child or the first child. So this fundamental counting principle allows us to come up with tree diagrams, or if we're just asked to find the total number of outcomes, then there's a real simple way to do that. Now let's think about it. What are your possible outcomes for the first child? Well, you could have a boy or a girl. So we've got 2 possible outcomes. What are your possible outcomes for the second child? Again, we're either going to have a boy or a girl. What we had here is not going to affect what we have here. So we have a possible outcome of 2 separate things, either a boy or a girl. Looking at number 3, what are the 2 possible outcomes for the third child? Well, the second child does not affect the sex of this child. The first child does not affect the sex of this child. So child number 3 could also have 2 outcomes, boy or girl. So if we're looking for the total number of outcomes possible, we're going to multiply these 3 together. 2 times 2 times 2. When we multiply 2 times 2 times 2 together, we get 8. So we have a sample space of 8 things. Now, if you want to figure out what those 8 possible combinations are, or if they ask you more detailed questions about what the outcomes are, we could draw it out. So this leaves me with this sample space. We could have all girls. We could have a girl, girl, then boy. We could have a girl, then boy, then girl. Girl, then boy, then boy. Boy, then girl, then girl. Boy, then girl, then boy. Boy, then boy, then girl. Or all boys. So these are the 8 possible outcomes shown in this fundamental counting principle. So if all they ask you is how many outcomes are possible, all we would need to put is 8. We would not have to do all of this. It's extra work. A lunch cart offers customers a choice of hamburger, chicken, or turkey sandwich on a Kaiser or wheat bun. Find the number of possible outcomes for the type of sandwich a person could choose. Okay, they have 2 choices, the type of meat and the type of bun. For the type of meat, they have 3 choices. For the type of bun, they have 2 choices. So we have a 3 choice times a 2 choice, which gives us 6. There are 6 possible outcomes for different types of sandwiches. A pizza shop has 3 crust types: thin, hand-tossed, and pan. 5 topping choices, 3 cheese type, and 4 sauce type. Find the total number of combinations a person could get with a pizza with 1 topping, 1 cheese, and 1 sauce type. They have a choice of 3 different types of crusts, 5 toppings, 3 types of cheese, and 4 types of sauce. So I would multiply all of those together. So that is 3 times 5 times 3 times 4, which is 180 possible combinations. In this one, it says a license plate will have 6 characters. The first is a letter, the second and third a digit, and the last 3 letters. If it is not possible to have any characters repeat, how many possible outcomes are possible for a license plate? All right, it tells us in the beginning it has 6 different characters, so I'm going to need 6 spaces. And what I'm going to do in each of these 6 spaces is put how many possible outcomes there are for each individual character. So we have 6 characters, that's why I drew 6 blanks. The first is a letter. Okay, if the first is a letter, how many letters are in the alphabet? Hopefully you know that that is 26. So we have 26 possible characters that we could use here, 26 possible letters. So we have 26 possible outcomes for the first character. The second and third are digits. Okay, digits are numbers. Hopefully you realize this. There are 10 digits, 0 through 9. Those are the 1-digit numbers that there are. Now, it does tell us it is not possible to have any characters repeat, so that's going to be important soon. Now, let's think about that. Are there digits in the letters? No, there are not. So, for this character, we have a possible outcome of 10 separate digits. For the third, it is also a digit. But remember, our digits cannot repeat. If we had 10 possible outcomes here, how many digits are left? Well, hopefully you're saying 9. If we use 1 digit in the second character, then we only have 9 to choose from for the third. For this one, how many possible outcomes are possible for the license plate if the last 3 are letters? Remember, no character can repeat. So if we had 26 letter choices for the first letter, we only have 25 character choices left for the next letter. These last 2 are also letters. We only have 24 letters left, and then 23 letters left for the last one. To figure out how many total possible combinations there are for license plates, we would multiply all these different characters or different numbers together. So the number of possible outcomes can get very large very quickly when you're dealing with the alphabet, since there are so many letters in the alphabet. A gun safe has a 3-character security code. Each character has to be a different number, no repeating. How many possible combinations are there? We're going to assume that when they say number, they mean a digit. So we have 3 numbers, so I need 3 spaces. For the first digit, we have a possibility of 10 digits to choose from. Since these cannot repeat, the number that we have to choose from for each of them has to go down by 1 each time. So this one we have 9, and in the last one we have 8. Then, to figure this out, all I have to do is multiply these 3 numbers together. So we have a possibility of 720 possible combination. A locker combination has 2 digits followed by 2 letters. None of them can repeat. How many possible combinations are there? So 2 digits followed by 2 letters. That's 4 blanks. The 2 digits, remember digits are numbers. None of them can repeat. We have a possibility of 10 digits to choose from for the first one. We have a possibility of 9 for the second because you cannot repeat digits. The last 2 are letters. We have 26 possible letters for the first one and then 25 possible letters for the next one, since there is no repeating. Then all we have to do is multiply these 4 things together. So we have a possibility of 58,500 different combinations. In the next one, you need to schedule a math, science, English, and history class for next semester. If all of these classes are scheduled every block for 4 blocks, how many possible schedules are there? Okay, let's think about that. We know we have to choose these 4 classes: math, science, history, and English. We have 4 blocks, which means we have 4 blanks. So in those 4 blanks, I need the possible number of classes I have to choose from. Well, for first block, I have a possibility of 4 separate classes. For a second block, I already chose one of my classes here, so I can't take that one again. So I'm only going to have 3 possible outcomes for the next one. For this one, I only have 2 classes left because I have picked 2 of them here. So I have 2 classes left to choose from. And then for fourth block, I've already chosen 3 of the 4 that I need. I'm only going to have 1 to choose from here. So the total number of possible schedule combinations would be 4 times 3 times 2 times 1, or 24. So that one wasn't too bad. Okay, the next thing we need to talk about are factorials. And in math, there is a symbol called a factorial. And you might have something like this that says 6 factorial. Now, what that does not mean is 6! It does not mean it's an exclamation point. Hopefully that didn't scare you too bad. It does not mean the same thing in math as it does in English, okay? So in math, what this means is we're going to take the 6 and we're going to multiply that 6 by every digit below it until we get to 1. So 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. And when we multiply those together, we get 720. Now, you can also do this in Desmos. So I want to show you how to do that in Desmos real quick. So here I am, I have an empty screen, 6 factorial. I just hit a 6 and the exclamation point, and you see there it's 720. So no special symbols or anything. You hit the exclamation point just like normal, and you get a 6 factorial or 720. For something like this, I'm going to put these directly into Desmos without anything else. So I'm going to put 3 factorial times 8 factorial into Desmos. When I do that, 3 factorial, make sure you do open up your keyboard and hit the times button, and then 8 factorial, and automatically it gives me 241,920 as my answer. And then for this one, I'm going to put 4 factorial over 5 factorial into Desmos. Honestly, that one's probably easy enough. You could do that without putting it in Desmos. Now they give you 0.2. We want these as fractions. We want we don't want to have to round, if some of them calls rounding, but we want these as fractions. So this will be 1/5. Always express these as fractions, please. That's how they were expressed in the original. So this would be 1/5. And keep in mind, this one is so simple. We could do that very, very easily on our own. 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. So the 4, 3, 2, 1 all cancel top and bottom, just leaving us with the 1/5. So you could probably really do that one in your head without even worrying about Desmos as well. But here's where they get a little bit more complicated. You may have some with variables, and you can't do variables in Desmos. The only variables Desmos recognizes is when we have a graph that we're dealing with. So for this, if I'm doing n factorial over n minus 1 factorial, that would be n times, and then the next term, the term 1 lower than n, would be n minus 1. And then the term lower than that is n minus 2. Then we could go to n minus 3, n minus 4, n minus 5, dot, dot, dot. We could keep going. But all we have to know is once we get to where they're going to start repeating, we can stop, because anything below that is going to cancel out anyway. So if we look at the bottom is n minus 1 times n minus 2, dot, 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 right? These both continue forever. So as soon as they start to repeat, we can start canceling. So n minus 1, n minus 2 cancels with the n minus 1, n minus 2 up here, leaving us with just n. So very simple answer for something that looked pretty complicated at the beginning. For this one, I want you to go ahead and pause the video, see if you can get this one on your own, and then in a minute I'll come back and give you the answer. So here, if I write this out, n plus 1 times n minus 1 times n minus 2 times n minus 3 times n minus 4, dot, dot, dot. And then the bottom one is n minus 3 times n minus 4, dot, dot, dot. I can cancel out anything n minus 3 or lower, leaving me with what's left on top. So the answer would be n plus 1 times n minus 1 times n minus 2. Sometimes with these, usually with these, you're only going to have 1 or 2 terms left. And it is okay to go ahead and multiply those together if you only have 1 or 2 of them left. But if you have something like this where you have 4, I would just leave it like this. There's no point in trying to FOIL all that together. That's just extra work for no need.